Supercapacitors are relatively new pieces of technology that aim to revolutionize how we store energy and charge for the various electrical devices of everyday use. Now, in order to understand what makes them so super compared to a regular electrostatic capacitor, let's go back to the basic definition of capacitance we learned in high school physics. A typical electrostatic capacitor is simply formed by two metal plates separated by an insulating dielectric. We can increase the capacitance of this standard capacitor by either increasing the surface area of the plates or by decreasing the distance between the plates. So first, how does one increase the surface area of the plates without them becoming impractically large? Eventually, we'd be dwarfed by our own devices. The solution is found in coating the plates with a highly porous carbon-based electrode such as graphene, which can have a very large surface area, as high as 2,600 square meters per gram. Secondly, in order to form the supercapacitor, also known as a double-layer capacitor, in place of a standard dielectric, the plates and the electrodes are submerged in a liquid electrolyte with both positive and negative ions dissolved in the solvent, with a separator that allows ions to freely flow. When a voltage is applied, the negative ions diffuse to the positive electrode, and the positive ions diffuse to the negative electrode. Additionally, due to something known as the double layer effect, at each plate, an extremely thin insulating dielectric layer is formed at the boundary between each of the plates and the electrolyte. The layer on each plate behaves just like the dielectric in a standard capacitor would, except these layers are made from a single molecular layer of polarized solvent, typically around only 5 angstroms thick. This creates two charged layers that each act as an individual capacitor. What we end up with is essentially two capacitors in series, each with an extremely thin dielectric layer. The capacitance of the supercapacitor can be taken as the capacitance of the two individual capacitors in series. The final aspect that makes these devices so super is the thickness of the insulators are on the order of a few angstroms, while the typical capacitor plates are separated by a few microns. Compared to batteries, supercapacitors have many large advantages. Chief among them is the fact that they can charge devices in a fraction of the usual time. They also have a very long lifespan and can be used many times over 10 to 20 years and still maintain about 80% efficiency. Additionally, they can operate at temperatures as low as negative 40 degrees Celsius. And even better still, they don't involve dangerous chemicals in the same way batteries do. So, the next time your hand is melting off from caustic leaked battery acid, you can think to yourself, gee, I wish I was using a supercapacitor instead right about now. On the other hand, supercapacitors haven't replaced batteries for everyday use just yet, since there are still a number of disadvantages that research hopes to solve in the near future. First and foremost, they are expensive. While batteries cost about $1 per watt, supercapacitors take 20. Secondly, while supercapacitors are high power, they are also low energy. That is, they can charge and discharge very fast, but they can't store much total charge. Lastly, the voltage on supercapacitors decreases linearly as they discharge, while a battery's voltage stays constant as it discharges. Still, supercapacitors are inching into commercial markets and may someday take their rightful place as the prime form of electrical energy storage.